Let us see how the zeros of a polynomial are represented geometrically for linear polynomial and quadratic polynomials. When we are able to find a pattern, we will state a theorem for zeros of a polynomial with degree n. When we draw the graph of p of x versus x, let us assume p of x as a separate axis y. For a linear polynomial p of x equals a times x plus b, or we can say y equals a times x plus b, where a is non-zero and a and b are real numbers. That is, graph of the polynomial p of x takes the form of a straight line. Let a be 1 and b be 3 in the above equation, we get p of x equals y is equal to x plus 3. For plotting a straight line, we need at least 2 points. Let us assume 2 different random values of x and obtain the value of y for producing an xy plot. When x is minus 4, y is minus 4 plus 3 equal to minus 1. When x equals to minus 3, y is minus 3 plus 3, that is 0. Also, when x is 4, 4 years is 4 plus 3 equal to 7. Plotting the line between any of these 2 points and extending on both directions, we obtain the graph. We find that the line intersects the x-axis in minus 3, 0. Hence, 0 of a linear polynomial is the x-coordinate where the polynomial p of x, that is y equals x plus 3, intersects the x-axis, that is y is equal to 0. In general, whenever we have a linear polynomial p of x equal to y equals a times x plus b, where a is non-zero, the polynomial has only one zero, which is the x-coordinate of the point where the graph intersects the x-axis, that is minus p by a, 0. In other words, it can geographically located at the point where the graph of the polynomial intersects x-axis. Let us proceed towards the quadratic polynomial now. The general form of a quadratic polynomial is p of x equals ax squared plus bx plus c, where a is non-zero and a, b and c are real numbers. Let p of x equal to y. Let us assume the values of a equal to 1 and b equal to minus 3 and c equal to 2 in the quadratic equation. We get y equals x squared minus 3 times x plus 2. For plotting the graph, let us consider some random values of x and obtain the corresponding values of y from the quadratic polynomial. We can thus obtain an xy plot. When x is minus 2, y equals 12. When x is minus 1, y is 6. When x is 0, y takes the value of 2. When x is 1, y equals 0. When x is 2, y is 0. When x is 3, y takes the value of 2. When x is 4, y is 6. And let us plot have one more point when x is 5, y is 12. Having plotted the graph, we find that the quadratic polynomial is a parabola. The curvature of parabola depends upon the values of a in the equation. If a is greater than 0, like in the present case, the curve opens upward. When a is less than 0, it opens downward. We can observe from plotted graph, when x equals 1 or 2, on both occasions, y becomes 0. These are again the points where the graph intersects the x-axis. The zeros of a quadratic polynomial are precisely the x-coordinates of the points where the parabola representing the quadratic polynomial intersects the x-axis. Now, depending upon the values of I, b and c, we can have 3 different cases. Firstly, the graph can cut the x-axis at 2 distinct points. Hence, there would be 2 zeros in this case. Secondly, the graph can cut the x-axis at only 1 point. So, there is only 1 zero in this case. And lastly, the graph does not cut x-axis at all. Here we don't have zeros at all and the graph is either completely above the x-axis or completely below the x-axis. In all these 3 cases, the graph can be anywhere with respect to the y-axis, and hence we have not explicitly shown the y-axis, since the focus here is to see where the graph intersects the x-axis. From our analysis, we can conclude that any quadratic polynomial, that is a polynomial of degree 2, can have at most 2 zeros. Let us proceed with a few examples. This time for cubic polynomials. Locating the points of the table on a graph paper and drawing the graph, we see that the graph of the cubic polynomial y equals x cubed minus 9 times x looks like the one given below by using some random values of x. Since the curve meets the x-axis in only the 3 points at minus 3, 0, 0, 0 and 3, 0, the x-coordinates minus 3, 0 and 3 are the only zeros of the polynomial. When the cubic polynomial y equals to 2 times x cubed, we obtain the following graph by plotting x versus y using the random values of x. Here we have just one zero of the polynomial, which is x equal to 0. Similarly, when we have a cubic polynomial y equals x cubed minus 2 times x squared, plotting the graph with random values of x, we find that the polynomial has two zeros, as 0 and 2 respectively. That is, the graph intersects the x-axis at two distinct points 0, 0 and 2, 0. From the above examples we can conclude, a cubic polynomial can have at most 3 zeros. In general, given a polynomial p of x of degree n, the graph of y as p of x intersects the x-axis at most n points. Therefore, a polynomial p of x of degree n has at most n zeros. Please pause the video, rewind and play again to absorb what has been covered in the topic. Let us proceed now.